Dear students, today we are going to talk about the current density. We will also talk about we will also derive the expression for current density in and electric related with the electric field. That is, we will find the expression for electric field in terms of current density, and we will also learn about what is relaxation time, and we from then forward further we will find the expression for drift velocity of the charge carrier moving in a conductor. So we shall be talking one by one about these things, but before we really start doing this type of talking, we must understand now, as discussed in the previous lecture, that a current is taken as a scalar at one time and as a vector at another time. The reason behind it is that, you see, according to Joule's law of heating, due to flow of electric current, that current heat is equal to H is equal to I square RT. You have learned in class 10. So here you see, if the conductor is fixed, time is fixed, that means R and T are constant. So what we are left with, the variable is current. So more is the current, more will be the heat. So it is not depending on in what direction the charge is flowing through a conductor, whether it is going up, it is coming back, no problem. Heat is produced invariably in both the cases. Means direction is not important, only amount of charge flown per second is important, and therefore we take the current as a scalar in this situation. But if we talk about a different situation, you see, whenever charge flows through a conductor, what happens? It produces some magnetic field around it, and that magnetic field is depending upon the direction in which the charge is flowing through the conductor. That magnitude is depending on the position of the point where we are going to find the magnitude of magnetic field produced due to flow of charge through a conductor. So that means here you see the direction of flow of charge is playing an important role while we are discussing the magnetic effects of electric current. So, and in other situations as well, we shall see that it is behaving, it should be taken as a vector quantity. The electric current in this situation must therefore be taken as a vector, because direction will dictate the magnitude of magnetic field, direction of magnetic field due to flow of charge through the conductor, and therefore we take the electric current sometime as a scalar and sometime as a vector. Now students, today we will talk about what is the current density. Current density is expressed by J, and we define it as the total normal current passing through the cross-sectional and unit cross-sectional area of a conductor. Means if we are say there is a conductor and some charge is flowing through it, then whatever charge is flowing per unit cross-sectional area of the conductor and along the direction perpendicular to the cross-sectional area, surface of the cross-sectional area. So that means here direction is being considered to be important. So along perpendicular, that is, we are taking I normal, means normal current passing per unit area, cross-sectional area, is defined as electric current density, and the direction is always along normal to the direction of current density is always along normal to the cross-sectional area of the cross-sectional area of the conductor. It is a vector therefore, and SI unit is ampere per meter square. You see, current is given in ampere and area, cross-sectional area is given in meter square. So we have ampere per meter square, or ampere meter to the power minus 2. Now we have to derive the relation E is equal to rho J, where rho is the resistivity we have already discussed, and J is the current density we have just talked. So how we are going to derive? We know according to Ohm's law, V is equal to IR, and also from this definition for current density, J is equal to I by A, therefore I is equal to JA. So we write I is equal to J normal current, and therefore V is equal to, for I we are substituting JA, so J is there, and for R we are putting the value rho L by A. This is for R resistance, rho L by A, and for current we are putting the value JA. So these two, when taken together, you see cross sectional area cancel each other, so that means it becomes V is equal to J rho L. Let us call it equation number 1, where J is the current density, rho is the resistivity, and L is the length of the conductor. Also we have the relation dV is equal to minus E dr, and therefore we have V is equal to E into L, where L is the length of the conductor and V is the potential difference applied across the conductor. So we are calling it equation number 2. On equating these two, what you see, that L and L appears in both the expressions, so they cancel each other, therefore E is equal to J into rho, and we also write it as J by sigma, because reciprocal of resistivity is called conductivity. Reciprocal of resistivity is called conductivity, and it is denoted by sigma. So that's all for the expression for electric field in terms of current density. Here you see electric field is a vector and current density is a vector. So this is very much now expressing adequately the electric field. Relaxation time, we define what is relaxation time. What is relaxation time? We must, before we talk about it, we must visualize the picture within the conductor. What is happening when the charge is flowing through the conductor? Usually you see, we talk about a solid conductor, and then in that case electrons are flowing from one corner to another, one end to another, and protons do not flow because they are held tightly fixed to the atoms, and so atoms are not moving because it is a rigid structure, and therefore only electrons, free electrons, are able to move from one place to another. And then while this is happening, means the charge electrons are moving in conductor, and if we talk about liquid conducting materials, then both the ions contribute in shifting the charge. That means negative charge, that is electrons, are contributing, serving as a charge carrier, and the positively charged ions, atoms, are also contributing in the shifting of charge, and therefore both have their own role in case we talk about liquid conductors. But that is a rare case, so usually we refer to the solid conductors. However, you can still talk about the liquid conductors. So in case of conductor, what happens? The charge carrier collide with among themselves, or they collide with the atoms or molecules lying in their path. Why they collide? Because once we apply some electric field across, once we generate potential difference across the conductors two end, the electrons are forced to move from one end to another, and as a result what happens? The electrons are starts moving from one end, say negative terminal, and starts moving towards positive terminal, and then the another charge carrier coming in its path, they collide with it, or atom or molecule coming in its path, they collide with it. So therefore collision is inevitable whenever charge carrier are moving through the conductor, and we take the average time between the two consecutive collisions. Average time means sometime it may the collision may take place after a longer time, sometime the collision may take place much earlier. So they vary with situation to situation, time to time. So what we take is, we take the average time between two consecutive collisions. That time, average time between two consecutive collisions of the charge carrier, is known as relaxation time, and we denote it by tau. You see tau. T is a scalar, its SI unit is second because it is time. Now we have to find the expression for, so we have to find the expression for drift velocity, means with what average speed do the charge carrier move through the conductor. We have to find the expression. Now we can, we very much know that equation of motion V is equal to U plus AT, and for that we take we take average, the total sum initial velocity of the charge particles to be 0. Why this is being said? Because once you have not applied any electric field potential difference across the conductor, what happens? The charge carriers are still moving within the conductor, but they are randomly moving, and there is no net movement of the charge particles through the conductor. Why we say this? Because if had there been charges moving in only one particular direction, then one end of the conductor may become negatively charged with respect to the another end, and so that means some electric field will be developed within the conductor, and which will pull back those charge which has been accumulated at one end due to some reasons. So that means this type of polarization of the conductor, when there is no external electric field applied across it, never takes place. So that means what? The average velocity of the charge carrier must be 0, means as many charge carrier are moving in one direction must be equal to same number of charge carrier moving in opposite direction, so that no polarity happens, no polarity is generated in the conductor itself. So that's why we take the total sum of initial velocity as 0, and once we take it V is equal to U plus AT, so U summation of all initial velocities when no electric field was applied is taken to be 0. So we are left with acceleration and time. Now acceleration is what? Force upon mass is acceleration. Force upon mass. And what is the force? You see, charge into electric field is force divided by mass. That is acceleration. We are talking about charge carrier electrons, so we mention it ME. That means for acceleration we write EE by ME, and for time we write relaxation time tau. Therefore drift velocity becomes equal to EE. The E, small e, is the amount, the charge carried by the charge carrier, and capital E is the electric field applied, and ME is the mass of the charge carrier, and tau is the relaxation time of the for the charge carrier, which is depending on the temperature, the density, etc. We shall be talking about it, the relaxation time, on what factor it depends in the coming topic. Thank you and have a nice day.